consultant for geoscience. Now we are ready to begin. Mustafa, please go ahead.
Thank you, Serena. Good afternoon, everyone. As Serena mentioned, my name is Mustafa, and I'm a principal geophysicist consultant with Landmark in Kuwait. So thank you very much for attending this webinar today. Today we're going to talk about how we can visualize and identify fault pattern and extract fault anomalies using fault likelihood attribute. We all know what fault likelihood attribute is, and we will talk about that in the next few slides. But before we move on, we will have a brief safety and a value moment. Okay. As we know that we are facing this coronavirus pandemic around the world, it is very important to adapt and accept this new reality. We and our children are now living in this new era of chaos and fear. And since we are mostly earth scientists in this webinar, so I will not hesitate to call this a Chronozoic era, as you can see in this image. This has been a game changer throughout the world. A new world has emerged where we have made some drastic changes, and it has put a great impact on our daily lives as we speak. Since prevention is better than cure, so please follow the instructions of the authorities and governments to avoid unnecessary exposure and contact, and stay away from crowded places as much as we can. So please stay safe, take care of yourselves and your families and everybody around you. Thank you very much. So in today's agenda, we will discuss briefly about the challenges we face in our approach when interpreting seismic and fault interpretation and data. The value of collaboration and visualization in our day-to-day work. Also, we'll talk a little bit about the fault likelihood, and then rendering and opacity and how we can extract faults information from these kind of data. And then at the end, I will proceed to the demo on the software. So what are the challenges we face when we as a geoscientists or interpreters start to develop our concept and understanding of fault interpretations and its complexities? And we can ask ourselves that how seismic data conditioning can improve our chances to image faults accurately, since there are various attributes and filters available for that task. And once we have the data ready, then we can focus on how to visualize and extract high definition fault information from those attributes. So in this case, fault likelihood. How we can understand the fault regime and networking, so we can have the detailed understanding of a fault model and quantify reservoir compartmentalizations. This point is especially important for the geologists who have to integrate faults in their reservoir models and further for the simulation models. How do we address fractures and lineaments? These fractures are sometimes very sensitive subject. Are these valid fractures or just processing artifacts or noise? And how do I identify and delineate those fractures? And how about the vertical resolution? And can seismic attributes like fault likelihood can identify areas of fractures, and can we characterize them? And I can ask myself that how can I reduce uncertainty when I'm picking faults, either automatic or manual? And we can ask ourselves as well that if those automatic fault interpretation algorithms, which are available in our applications these days, are they mature enough to overcome and understand the geology and structure complexities? But this particular workflow will allow us to use a volume rendering and opacity. And with this technique, we can understand the overall fault pattern and bring forth any hidden features and small scale faults which normally are not very visible on the map and the section viewed during our routine interpretations. So I would say that the whole purpose of looking into all those challenges and complexities and putting some efforts into them are that we want to do our due diligence before we go and drill a multi-million-dollar well and mitigate all the risks associated with it. So this is very important to analyze that at the end of the day, what is our goal and what we can achieve for our company. I want to emphasize on the value of these workflows and also on the importance of 3D visualization in the upstream oil and gas industry. And I'm sure lots of people here have been using these techniques already. 3D visualization is now part of the day-to-day work for any interpreter and geoscientist. However, it is still not as popular as 2D map and section view displays on interpretation softwares. And when it comes to the standard fault and horizon picking, very specifically, mostly interpreters still use and prefer 2D map and section displays on their softwares, whether it be DSG or whether it be Petrel or any other software. Now, with the invention of high-end graphics and machine learning neural network-based predictive algorithms, we can now interpret and visualize much larger seismic volumes and earth models quite easily in high resolution and while rendering the data in the memory. And as we see that with the introduction of cloud, I think it would be even more important in the future to utilize these technologies in a very high degree of technologies. It's all about changing the perspective and seeing the other side of the picture. For example, an interpreted fault seen from the map view would look entirely different in a 3D view because we will rotate it, we will look at the plane or triangulations, and we will look at its segments and analyze it from all directions to understand its geometry. And then it will tell us a totally different story about that fault. So, as a testament of that situation, um, I can say that almost all the international and national oil companies like KOC, excuse me, KOC, Aramco, ADNOC, Petronas, and you name it, also international oil companies, they have those high-end visualization facilities to collaborate and integrate their asset teams. And I had the privilege to work with some of them closely on such projects. So the level of investment these companies have made so that their geoscientists can sit together and understand the subsurface structure more precisely. And the value comes to the point where we geoscientists and interpreters do our work more efficiently and effectively and save time and cost. So obviously, in all this situation, we come to the point where collaboration with other discipline within our workplace is quite important uh, to manage all our subsurface workflows. Okay, next slide. Uh, what is fault likelihood? So I'm going to talk a little bit on that. The fault likelihood attribute was developed by David Hale. He's an American professor and a geophysicist in 2013 from the Colorado School of Mines Center for Wave Phenomena department. It is a fairly recent development within our geoscience applications, and it is a very useful attribute to visualize and understand the faults and areas with possible fractures, subject to the fact that the data conditioning and amplitude balancing was done properly. And I can see that almost uh, all the previous attributes have been replaced by this fault likelihood attributes, like we can say semblance, discontinuities, and other attributes, or chaos. They all have been replaced by likelihood. People now prefer thin likelihood or likelihood attributes. The data values in these attributes are in the range of 0 to 1. 0 means less likelihood, and 1, as we approach 1, the likelihood of fault increases. This attribute is developed aiming to capture and delineate fault and fractures in the area of interest. Rendering and playing with opacity will make us see the internal structure of the volume and then allow us to differentiate between the faulted areas from the clean areas. And I will talk about that in the next few slides. These kind of model and data visualization can help the asset team to decide the well entry path in the overburden and in the reservoir zones, where mostly we have shallow faults and channels and other features, and by the way, which every driller would like to avoid during the drilling process. One of the example I can give you is where we have used this kind of data exclusively to do our work is the project is a loss of circulation incident project, where we used fault likelihood volume and fault likelihood data to mitigate the risks for mud loss incidents and try to predict that this area we should avoid, otherwise we'll have a total or sphere or partial mud losses in the wells. So that project was a success here in Kuwait. So it's quite a important thing. Okay, this slide which shows how the core rendering and opacity enhance our understanding of the structure and features within the attribute volume. We can segregate and remove any unwanted features. We can segregate gas chimneys, shear zones, karst features, and salt bodies, and other amplitude and AVO anomalies using this very simple technique. Either we can visualize the full volume or the sculpted volume between the top and the base of the reservoir, or any two given horizons if we have. And you can see, as you can see in this slide. For the reservoir characterization, this is also critical and important to understand the fault and fractures at the reservoir level. And volume sculpting can help in this task because we can restrict ourselves within the reservoir zone, and then we can analyze and characterize those faults and fractures within these two horizons. Okay, so what we have here is a simple thin likelihood volume. This thin likelihood volume is one of the output of the fault likelihood attribute process. We normally get 6 volumes out of it, and I can explain that in the Q&A or in the demo. So this thin likelihood volume includes the area from the main sandstone reservoir of the Middle Jurassic. This seismic actually originally from is a demo data, so originally from Hadrian Field in the North Sea, and the field boundary is shown in the dashed polygon, as you can see here. The white and the grayish area on the seismic indicates the area with the least likelihood of having a fault, and the yellow lines or the orange lines on the cube on the seismic volume indicate the faults and some form of lineaments. After I change the display setting of my volume, well, now I'm looking at the GeoProbe window. So after I change the setting of the volume to a rendering mode, and I have to put the volume into a rendering memory mode, and then I can draw my opacity curve, which you can see on the upper right corner of the screen. By eliminating the zero values, and the zero values means the values with colored gray, I can then display only the faults, which gives me quite an insight for my overall fault pattern. And suddenly, a lot more features will be available. And I will just show you now, if you can see in this image. Right. So this fault pattern and image comes out after I display the data in the rendering and eliminate any less likelihood fault areas. Now I'm looking at a bigger picture, and although this is a smaller part of the seismic survey, but imagine if you have a bigger seismic volume and you can visualize it, all the faults, all the fractures, all the lineaments in one go without even interpreting a single fault segment. And then you can have a good idea that how exactly my fault pattern look like. You can understand the geology and the structure and everything else. Okay, so based on our opacity curve and how aggressive or lenient we are in applying the opacity, the faults will be displayed accordingly. So if I have lenient opacity curve, or I can cut this yellow and the reddish areas more, and obviously my faults will be less visible. Now at this stage, when I have the thin likelihood volume with its rendering mode activated, it is still a volume. Basically, it's still a seismic volume or thin likelihood volume, and there is nothing much we can do with it but to visualize it. I mean, I can only visualize it, and I cannot do anything else with it. And you can ask that what's the point of doing all that visualization? So I can tell myself that, well, now I'm more curious. to do more, and I want something out of it. So obviously this is our nature to do and bring something out of it more. So now I want to create those faults which you can see on the screen in this yellow screens and images. I want to create the fault segments if I can, right? So therefore, based on this need, I would open up the Geo Anomaly Manager from GeoProbe and input my thin likelihood volume as an input, and also I will input opacity curve which I created, if you can see on the lower right, lower left, uh, as a selection criteria. So I'm telling the software that please select from input volume this opacity and create anomalies out of that. So once all the input parameters are selected, we can then run the process of creating anomalies out of this volume. And I will display this image now. So after running the GeoAnomaly Manager and process, this situation, these anomalies are created. So now you can see that almost 70% of these faults have been created as a voxel-based objects, and they can be saved in various other formats. It is always better to work on a smaller vertical range in time or in depth because they work both in PSDM and PSTM, as otherwise we will see overcrowding of faults and unwanted features. So we should restrict ourselves within our range and area of interest or the vertical zone of our reservoirs. Otherwise, obviously, there's a lot of information in any given seismic volume, so we will otherwise be very confused. And I will show that in the demo as well. So this is the output I get out from running the fault likelihood and GeoAnomaly Manager. So you can say that what is a geoanomaly? Maybe this is something new, a new word to hear, and how they are created. Well, geoanomaly or geoanomalies are voxel-based features and objects which can be extracted from any seismic data by giving various selection criteria like amplitude, range, and opacity curves. So once we extract these anomalies, and which can be faults, which can be channels, discrete sand bodies, and so on, and as per our opacity settings, we can save them back into geobodies. We can save them as a faults or fault segments or fault planes. We can save them as point sets or geoshapers, and we can also save them as seismic volume. So you can imagine that you interpret or you extract those faults and then you save them back as a seismic volume. And then these are the faults you're only looking for, and then you can go back and then interpret them, or you can have it as a display option for you guys. So I can save these faults in the OpenWorks database quite easily once I create them. And I can use them in any other workflow which I have in my DecisionSpace, which I have in my OpenWorks, or any other application which I have within Landmark suite. Especially as we know that these days people are using those fault frameworks, faulted framework models in the velocity modeling. And velocity modeling, which are faulted velocity models, they are very much appreciated because obviously there are a lot of interest with the geoscientists to see how the velocities behave when there is a fault, when there is a thrust fault, when there is a reverse fault or graben, or all those kind of structural complexities around that. So we can also create these faults or convert them into polygons as a fault polygons using obviously the framework, and use those from there onwards. We can take them to the geocellular model. We can eventually use them in the reservoir simulation model as well, and also in the reservoir static modeling as well. And all this process would significantly reduce the time which I was used to spend on understanding the overall fault network and interpreting faults, segments, and fault polygons. And also we can do the well planning quite easily, knowing the fact that all my hazards are sitting and in front of me, and I can see each and every fault and lineament. So I can design and plan my well safely. As a geoscientist, I can at least give a nice subsurface location or a horizontal section to the drilling people. Uh, and lots of people have asked over the last few weeks that can we handle thrust faults or reverse faults in that? So my answer is yes, absolutely. We can handle reverse faults because in DecisionSpace Landmark, there is an option and there is always a way to handle multi-Z values. And obviously, based on that, we can create seismic fault likelihood attribute, and also we can extract geoanomalies like this on the for the thrust faults. And just to let you know that this technology or this methodology is not very new. It's old. A lot of industries uses it. So medical industry use like MRI is one of the technique they use, and they use voxel imaging, and also Minecraft in the gaming industry. If when the kids play games, they also use this voxel-based technologies and imaging to develop those games. Uh, so these are the one, and obviously there are a lot more features we can show, but we can show that in our demo. So after creating everything, I can come to a conclusion that with this very simple technique and workaround, where we can visualize and enhance our understanding of the data and our fault regime, that how from a thin likelihood volume, we can visualize the full field fault network in 3D, giving it a different dimension, and create those voxel anomalies and voxel bodies, and then save them back into faults and some other formats used, and then use them in our modeling and other workflows. And within all that process, the time I spent is probably less than 2 hours, right? If my likelihood already is with me. So this is one of the important things, but likelihood takes a bit of a time to create. So once you create the likelihood, you can complete the whole workflow in less than 1 hour and at least get a bigger picture of your fault network. And obviously, faults are sometimes complex. Sometimes every field, every volume looks different in terms of what the faults they have. So obviously, this is very important for a geophysicist because I go through the same phase. So I understand that it is one of the important things which any geophysicist would like to have and see at least, and have a visualization of the fact that how his fault model looks like before even he go and interpret the very first segment on his seismic volume. So that's all for today presentation. There is a small movie I have made, so I will just run. So please take a moment to look at that, and then we will go to the demo, and then we will have a Q&A. So sorry. Yeah, so this is the whole process. You can see that how it is done without any other menus, with just a pure rendering movie on the data. And I can give you a bit of commentary on the back end. So now what I'm doing is trying to change the colors and adjust colorings of the volume so I can have a better output. So I'm interested in those yellow lines rather than the gray area. So now you can see that suddenly my faults are visible, uh, and uh, and all the gray areas are gone. Now I will also try to make sure that my resolution of those faults are higher, so I can at least have a good look. So you can see that they have been sharpened, and all the features and everything, which was anomaly, which was faults, which was lineaments, fractures, maybe are there. And now at this stage, after running the geoanomaly, I have created those faults in less than 5 minutes, right? So even if we go and create a fault in any software, it will take us more than half an hour to at least visualize one fault. Now here I can create it. I have created these in the next 3 to 5 minutes max. So yeah, so this is the movie, and I will show that in the demo as well and demonstrate how exactly it is done. So thank you very much for listening to the presentation. So now I will go to the demo of the software, and we'll see. So we have our GeoProbe. This is the GeoProbe software. So here, what we see here on the screen is a kind of display. So I will just simply switch off a few things so we can see the whole simple picture. Right. So this is my simple amplitude volume, seismic amplitude volume, but I have co-rendered and you can say combo mumbo, which the term we use here, with the thin likelihood volume. So you can see all the lineaments have been enhanced and increased. Let me switch off the wells so we can see the seismic alone. So if I just pan through quickly, you can see the faults very nicely and sharp, and the discontinuity between the faults are quite clear. Also on the vertical section display, this is my reservoir, as I mentioned. So as you can see, the faults definition is quite nice, displacement, and I can see QC as well, that the faults are there where they're supposed to be. So there's nothing which gives me an indication that there is no fault and yet the software have created a fault. So you can see in this area there is a fault. Uh, the software will create the fault as per the tip and the azimuth of the fault when it moves and when it turns and twists around within the seismic volume. Okay, so if I go and display now my thin likelihood volume. So this is my seismic amplitude with overlay of thin likelihood. I'll switch off this data, and now I'll simply go and create show you the thin likelihood volume. Thin likelihood volume, which is one of the output of the fault likelihood process, and I would simply go and display my seismic data with a color bar for this volume. My color bar is adjusted according to my requirements, so I can choose any color. I can use any color bar. It's up to you guys. So, but before I go, I must change the display mode of my volume into a rendering mode. So in GeoProbe, we have an option here. It's called Draw or Style. So when I go to Draw or Style, I can have multiple options. Right now, I am at opaque because I'm looking at the full volume. But now I will click it to Volume Render, and volume render will still give you the full volume as you saw previously. But now I have an option to use my opacity curve, either vertical or horizontal line, or the curve I can draw by hand. So now I will show you that this is the total histogram and the data values of my fault likelihood, thin likelihood volume. And you can see that this thin line is indication of those zero values, which indicates that there is no likelihood of having a fault. So now if I just quickly draw my fault curve, and now you can see that with this, just removing this thin line, simply, I can display my fault. So with this color manipulation, either I can do proportional or symmetric. So I can see which colors I want to see, which color I want to enhance. So you can see the faults which are in between these faults, major faults, can be shown as a gray, and so on and so forth. So there's a lot of choices of colors you can change. However, I will try to just display a little bit less, so I can have this, and I also I will try to reduce my seismic volume, so I can simply look at the area of interest, which is my major field, this is my field area with with accumulation of oil and gas. So now you can see, because previously you normally used to look like this as time slice on your seismic volume, even in a 3D mode, even in a 3D visualization window of any software, you would still look into this kind of situation. However, now with this kind of technique, I can give my faults a third dimension, or so to speak, a fault in a 3D without even interpreting it. So now you can visualize how important this fault structure might be, and where I can place my well, and how I can interpret those wells, and which faults are connected, which faults are sealing or networked or crisscrossing, and so on and so forth. So there's a lot of obviously geological information you can get out of this big picture. You can look at the big faults around here. So, but again, as I mentioned in the presentation, that now anybody can ask that, okay, what's the point of having that? You can visualize it, you can just go around and do some more techniques and stuff, but what to do with those things? So, so I have obviously an answer to that. That well, I want as a geophysicist that I want this fault. If you can see my mouse cursor, that I want this fault, or I want this fault or this fault to be created as a physical fault segment, which I can go and save it into database and then do some other work with it, just not only to visualize on it. So for this thing, I have this GeoAnomaly manager on this icon, as you can see, and with this tool, it's an important and nice tool we have here. So I can give my input data, as I mentioned, that my thin likelihood volume. I can also mention my top and base of my reservoir to restrict my seismic anomalies or these fault anomalies within my reservoir zone, or I can run the whole volume as it is. And then to select the range for the picking of those attributes, I can give the anomalies, those opacity curve, because this is the same opacity curve I used just to visualize this data. So this is the same curve as you see. So if I go and be more aggressive and cut more data, so you can see I will only look like this. Anything which I do will have obviously be effect and impact on the displays and visual displays of your thin likelihood volume. So obviously I have to be very careful on how much data I cut, how much data I want. So as we see that most of the data is sitting in here, so I will just actually use this simple data and curve and use this as an input and this opacity curve, and I will leave the rest of the volumes into rest of the parameters as default, so we don't change anything too much. And I'll use maybe 26 phase or 6 phase of connectivity of the voxel images. So, and once I go and create that data, it will take some time, obviously like 3 to 5 minutes or 6 minutes maybe, depending on how big and small your seismic volume is. So that's why I will not run it now, because I have already created for you guys. So we'll see how it looks like. So the data I created was for, I think, this much area. So when I go here, when I go create, it will give me this kind of image. There you go. So, and the one you saw in the slides. So the moment I click create, it will took me 5 to 6 minutes, and then it gave me this kind of data. So if I go and switch off my seismic volume and or maybe make it an empty volume, so I just only see my anomalies which were created from this seismic data. Now you can have a good understanding of how those faults are created. Now obviously you can ask that not every fault has been created. Obviously that's correct, and not all the anomalies were picked. Very true. Now that is because maybe my criteria is a bit too tight, and maybe I have to loosen it. I have to give a bit more information and maybe change the parameters. So it's all doable. Obviously, this is not something that we cannot do with that. So I can even go and I can say my minimum anomaly should be 10. So or maybe 100. So this way I can pick more. So the lowest I go, I can pick more from those data sets. So here we have all the faults, and you can imagine that these fault or these anomalies are grouped as uh, as anomaly in the anomaly manager. You can see here they are given color. I can color them with my attribute, with my seismic color, or with individual colors, or with same color. So it depends. So that is there. Also, you can see that I can display them. Let's do this and I can display them individually, and I can analyze them one by one, that how these anomalies look like, and how I can uh, instead of QC them or maybe do with other things with these things. So So what I'm going to do now is create, let's say I have this fault or this fault, let's say this fault, right? So this anomaly I have created, and you know that it took me 5 minutes to create this fault, geoanomalies. And now I take this fault, I want to take this fault into my database as a fault segment. So there is a button here which says select anomalies to sell or select, create easy faults or point sets. So when I click here, I give my system, so I call it ONGC fault number 1. All right, so I call it orthogonal projection X and Y, rib direction Z. I can call this ribs 25 ribs. So all the parameters are set. We can change based on your choices, obviously. And I go create. The moment I go create, what it does is it creates me a point set. So okay, let me quickly go and switch off my anomaly. So because I have already now fault, so I can switch off the point sets. We can see. So this is the point set he creates, and as well he creates me uh, the the fault. Very quickly, he has created me a fault. Now this fault is here, as you can see. I can go and save this fault into GeoProbe as a file or into OpenWorks database, and then use them in my interpretation. This is just as a simple fault as we can have, uh, or which we interpret at the end, and we can say that this fault. Let me do this. Draw style opaque and volume. So you can see that how the seismic fault from these anomalies have been extracted in less than 1 minute. So the fault is there, as you can see, and maybe you have to go do a little bit of edit at the end of the day if you have to, but I think 99% it fits on the data. So this is what we do, and but then you say this is just one fault. How about all the faults? So we can also do that and uh, create the fault sets out of those anomalies. So let's say if I go and come here, so I have multiple other options to create. So you can see I have an option to create geobody. I have option to create uh, geoanomaly or geoshells. Option to create seismic volume out of those data sets or point sets. So I think I will, and also maybe I can create those as a surfaces or point sets too. So what I will do probably is I will create those as a geoshells. So now geoshells are created. Now geoshells is another form of an object or kind of data sets, which is also voxel based, but they can also be used into DecisionSpace, into any other software. They can be converted into tsurf and so on and so forth. So going back to the software here. So let me switch off these guys. And now I have the geoshells with me, uh, as you can see. And also, maybe I can go and change the colors to Z. So now you can see these entities and these data sets are now available to me. So almost, if not everything, but I believe this was my range from vertical range. So obviously it didn't create anything above, but you can give all the way wherever you want, so it will create accordingly. Likewise, I have created quite a few of those anomalies just to visualize and just to understand how the fault pattern looks like and works. So let's say in this case, uh, uh, these anomalies were run from for top and base of the reservoir, and you can see that they are exactly as within my, you can say, oil water contact. So anything beyond that, I'm not picking anything within oil water contact within the top of my top reservoir. Between the top and base, I have picked up all those anomalies and fault data. So if I come here and visualize my surface, so you can see that those anomalies were created between these two faults, between these two surfaces. Now, and I can take them as just I mentioned, create a fault out of them, create any other data sets out of them as well. One thing I want to show again quickly before I finish, and is that we have a seismic volume here, and I can actually go and visualize it in any other way. So maybe yeah. So this was another volume which I created from those faults which I picked at the end of the day. Yani this was the anomalies converted back into as a volume, and I can take this volume back into Petrel, into DecisionSpace, into Kingdom, or any other software. So then you will have a fault volume, which you can only go and pick fault or create out of that more faults and stuff. Uh, so this is quite it. Another important thing, I think the last thing which I would like to mention before I go is, just let me go back here. X, Y. Okay. So before I go and before we do anything else, I would like to say that this is very important to understand that how I can use those fault information, how I can use those geoanomalies and plan my well at the end. So if I come here, let's say, close this data, and I just simply go and say, let me go and open the well data. Yeah, so this is my wells in this field. You can see mostly wells are drilled and planned between the major faults. So let's say if I go and create a well within my reservoir, so I can simply go and build well, and I'll just simply start drawing. And I know that it might be a bit hassle. I can make sure that I go and click on my z values, my data, and there you go. So the well, let's say this horizontal section is only I'm interested in, and the rest of the section from surface will be taken care by the well planners. So now I can have this well, and I can go and say add well, and so I can go and call it number 2. So this I have created 2 wells, and I'll change the properties. Space cylinder, right? So you can see these 2 wells, pink and green, were the wells I created for this demo. Right. So very easily I can place my well exactly where, as a geophysicist, I would want, and this gives me a great comfort and obviously power to visualize my data, and as a geophysicist I can plan my wells accordingly, according to my interpretation. So you can see there are quite a few wells I just drew as per our data, and if you have to uh, go through the fault, you know how you can go through and from where you can go through with the minimum risk uh, uh, to this well, and to minimum losses you may have at the end. Uh, Again, as I mentioned, that all these data sets are highly integrated. I have brought up these faults which I have created, and geoanomalies, these geoshells from this GeoProbe to DecisionSpace, and I have used those faults, which you can see here, which is actually created from those geoanomalies in less than 5 minutes. All 1, 2, 3, 4, 5, 6, 7, 8, I think 10 faults I created from those geoanomalies in less than 5 minutes, uh, uh, and brought them into GeoProbe, to DecisionSpace and in OpenWorks. I have used those faults to create these polygons. So you can see that the workflow now is getting into shape, that from just simply seismic volume to geoanomalies, and from geoanomalies to seismic faults, interpreted faults, and from there onwards I have this data where I can have a polygon for each of my intersection. So you can uh, uh, do your mapping, you can do your gridding, you can create your structure models and stuff like that. I have created a structure model, a structure layer out of it to from this 2 horizons or 3 horizons I have. Also, I have so let me switch them off. I have also created a geocellular model, which is technically an input for the geo reservoir models for the geologist who can add properties to the well and facies. So I can give him now this model, and he can simply use this model into his reservoir modeling process with all the faults, with all the geophysical faults, with all the compartments, with all the hazards identified, and all the complexities which geophysical anomalies and complexities we may have. So geologists now have all those things in this data, and you can see that now all the information is highly integrated. Or I mean, this is something important, and I think you all know that this workflow is simple, although, but it kind of contain a lot of punch and value for an geophysicist. So I think with this, I will finish the demo as well. And if you have any questions, I would be glad to answer those things. Serena, so if any questions, anybody, if you have, please do ask.
Yeah, we have, hi, Mustafa. Yeah, we have some questions in the control panel.
Okay, just a second. So way to create, okay, so the question is, okay, there are a lot of questions. So what is the use of multiple output generated during fault likelihood attribute when we are more comfortable with only one? So I think the answer to this question is fault likelihood process or attribute, which is available in within DecisionSpace. It has, I can say, it has certain parameters we can set, but the outputs we cannot control. The outputs are automatically embedded in the process, and there are 6 outputs which it is outputting for us. I can count for you. Is one is fault likelihood volume, another one thin likelihood, then tracking, and then dip and azimuth, and also we have a structural oriented filter volume. The one I used here was thin likelihood, and also maybe in DecisionSpace I used fault likelihood as well. So these kind of information is by default coming through the software itself, so we cannot control it. Okay, so any other question?
Yeah, there's one. There are a few more. One of them is,
So
how can we generate horizon-bounded likelihood volume?
horizon bounded likelihood volume. Actually, for likelihood process, I can show you quickly on in here. The fault likelihood, which when you create, it doesn't give you the option to input your seismic horizons, so you don't have the option to sculpt your data. However, once you create the seismic fault likelihood volumes and processes, you can take the input and you can do this. And I can show you here quickly. So if I open up my uh, data, yeah, so this is my fault likelihood volume, and I don't want anything else. So if I go and again do the same thing which I did in GeoProbe and input my top and base of the reservoir to use and to sculpt the data within the horizons, within the 2 uh, surfaces, I can easily do that. And you can see that I have these 2 data sets. Let me go make it a bit bigger. Right. So this is the same kind of information you're looking at from the top and base. And then once I am in this mode, I can go and quickly draw my opacity as I did before. And you can see that I'll keep starting and keep looking at the information which I can interpret in various ways. I can identify channels, I can identify karst features and any other features or anomalies you're looking at within your data or within your reservoir. I can do that, and I can visualize my data much more precisely and better. Yeah, so yes, we can do that. So generation of likelihood is a full process. It contains what it needs a top and base range. So 0 to 5,000 seconds, 0 to 10,000, 2,000 to 2,500 milliseconds, or whatever you have in time and depth, and also the area of interest, the spatial area of interest. But once the data is created, you can then do whatever you want with that. So any next questions?
All right. Yeah, the next question is, can well planner work in time domain?
Well planner can work in time domain within the DecisionSpace domain. Yes, we can work only if we have the velocity model activated in the backend, because velocity model will enable the geoscientist to work on the depth domain, because it is automatically converting on the fly. Any data we create in time, it will be converted in depth using that velocity model. So yes, we can do that.
All right, the next one is where to create fault likelihood volume in GeoProbe, and can you discuss about the parameters for FLH volume preparation?
Okay, so we cannot create the fault likelihood from GeoProbe, because GeoProbe does not have option to do so. This option is available only in DecisionSpace, which I just showed you, that if you right click on your seismic volume in the trace calculation and in the seismic attribute generation, we have this process within attributes tab. It's called fault likelihood. And then the parameters what we have is horizontal fault size, which is strike direction, and also we have vertical fault size, which is dip direction. So we can change only those two parameters, which can give us some kind of control that how much faults I'm picking, what kind of resolution those faults might be having, and how much. Basically, this is a scanner, because this process will take the sample, each and every sample, scan it, and then create a correlation between the two consecutive seismic wiggle traces. So if he finds a break or a discontinuity between the two traces, he will create those likelihood value on that area. So obviously this depends on how much faulted areas you have and what kind of seismic volume you're looking at, and certainly your seismic input volume depends a lot. We have to, as I mentioned in my presentation earlier, that we have to condition and filter those data sets, and there's quite a lot of filters available. So you can see that there is two filters we have available. It's called preserved fault or smooth fault. They're structural filters, and they're very important if you have to run and recondition your seismic input volume, original amplitude volume. Then I would recommend that we run preserved fault or smooth faults, or at least if you don't want to do that, have the balanced amplitude balanced, and it's amplitude as a balanced values. So in this case, just like this here, minus 15,000 to positive 15,000. Rather, sometimes if I have like this, so my input volume will be bad, and my output volume also will be not very sharp and visible in this case. So only DecisionSpace can create the fault likelihood and the parameters I just mentioned. Okay.
All right, the next question is, are we able to carry this output into my NFN module and workflow?
Very good question. Yes. The point I'm trying to say here is if you have the NFN license, right? So Natural Fracture Network, Natural Fracture Network can use the secondary data, because first original data you have from the fracture well data, which I know you know what I'm talking about on that. So you use those data as an original input from your well data, and then you want to supplement an additional input, so to have much more control on your larger area of interest, because the wells are at a particular place, but seismic is big, obviously. So these kind of information can be used. And as I just mentioned, that you can use the secondary data uh, to uh, to do this kind of information. I don't have the well data right now. Obviously, I cannot use. But if I click here, I go to this button, and it will open me a tab which will ask me to input my secondary fault likelihood information. Now that only can be done by uh, this process, by adding or blocking seismic fault likelihood on your geocellular model. So when I right click on here, it will give me, you can see that I have blocked the values of fault likelihood on my geocellular grid, and that grid information will be given to the NFN as a secondary input. So it's not the direct fault likelihood, but obviously direct likelihood can be incorporated into the geocellular model, and then it can be given. So like just like that, this is a sweetness grid. This is a fault likelihood grid. So you can block any seismic attribute on your grid, and then use it as an NFN secondary input. Okay.
All right. The next question is, this specifically is aimed for fractured basements and tight continuous reservoirs.
Okay. Um, Again, this attribute particularly can be used anywhere. Either you are in a very shallow, let's say we have a heavy oil area in Kuwait, so we use also this thing. We have channels in somewhere in the Upper Cretaceous. We use that also to identify channels and other features, and we use this for any other area or within the vertical zone of the seismic area section. So for fracture basements, yes, I mean if you want to identify fractures, and I can tell you that some people obviously will doubt on this statement, but I'm confident, and I have tested it in a project here live in Kuwait on within one of the data sets for KOC, uh, that the fractures which we identify using fault likelihood are the areas of fractures which actually the company, the team or the asset team has also identified. So we from the seismic and the whole asset team and the field development has also done the same thing. So we have come to a conclusion that fault likelihood can identify the areas of fractures and the zones of within the field or within the reservoir which might contain fractures. Obviously, faults are very understandable and visible, but fractures are sometimes, not very visible, or is like an area which you can't interpret properly. So these kind of information we can definitely have I would say 75 to 80% of accuracy and confidence. Uh, and then we can, but the only thing we cannot do is we cannot characterize those fractures, because we don't know which fracture is open, which fracture is closed, what is the orientation of the fractures, unless we have the well data associated with it. But and I cannot pick those fractures as individual faults unless until I go very small scale seismic volume and in all those testings. But yes, I mean there's a lot of options we can avail, but the fractures uh, can be detected. I would say with either it's a basement fracture, either it's carbonates, either it's shale, either it's limestone, sandstone, whatever it is. We can somehow, with some degree of accuracy, we can identify those fractures. Okay.
All right. The next one is, what is the difference between preserved faults and smooth faults in structural filter process?
Okay, so the data I showed you here, this seismic volume, uh, this amplitude volume you're looking at, was run uh, and was actually so one of the attribute was run on this seismic volume, and that attribute was preserved fault. So this is what it looks like. This is what it does with the seismic data. So it creates more sharp continuity or discontinuity within the seismic volume for the faults. So this is what it does as preserve fault. But he preserves because if you go and look at the seismic volume, sometimes in the section view, sometimes the faults look curve and it's going down the downthrown side, and then it goes and it make a nice curve back to the normal in the other way. So what it does is create the sharp boundaries between the throw and the heave of the fault. So this is what it does. I think also smooth faults, he will smooth the faults, remove a little bit of kinks from those areas, and still it's gonna give you a nice visualization of those faults which you see on this amplitude volume. And this volume can be input for my fault likelihood, because it will be even much more sharper in resolution for that reason. Okay.
But how are the volumes generated in fault likelihood used?
Sorry, can you repeat, please?
How other volumes generated in fault likelihood are used?
Okay, very good question. Just like any other volume you use, and you have to have a plan that what exactly you want to do. Uh, I can say that the fault likelihood, as I mentioned, creates 6 outputs, and one of those outputs is I can show you here, and you can just see for yourself. So this is if you see the screen and see the selection of my volumes, so you can see that this is full fault likelihood. This is fault likelihood strike. So this is a strike volume, and this is also a structural oriented filter volume, thin likelihood, and this is also my strikes, uh, and this is my tracking. So basically, we can use them like any other way. So for in front of you, I have used 3 volumes already. So let's say this volume, sorry, here, this volume I just used. This is fault likelihood, right? I used opacity on that. So if I clear this, this is the fault likelihood. This volume is this one, I guess. This is thin likelihood, right? And I can put in display tracking, which will be probably look same exactly. Um, I don't have the okay, maybe I can put here as a strike volume and show you exactly what it might look like. So just 1 second, please. Okay. Yeah, okay, so yeah, in this survey, I don't have likelihood, strike, thin. Yeah, so not in this volume. But as I mentioned, sorry, I don't have the exact volume in this data, in this area. But you can definitely use this tip volumes and strike volumes can be used as per their names. Obviously, there are dip volume will give you the dip of the data. If you have a dip volume, it will give you that most of the faults are in this direction. So he will create a small dipped features along these faults. Which so in this case, I don't know what the dip of this fault will be, but whatever it will give you the indication that these faults are in this dip direction, and so as for the strikes. So all 6 volumes have a usage, and they are used actively. But I think the most we use is thin likelihood, fault likelihood, and tracking volume. Tracking volume is used for automatic fault picking, which is called AFI. So as I mentioned in my presentation, that automatic fault tracking tool, which is available in DecisionSpace, can accept the thin likelihood volumes and also tracking volumes. So you can create and automatically create faults and fault segments. What I have done here is I have not used this algorithm. I have used a different way or different technique, like using opacity and rendering to visualize and get the faults by myself. Okay.
All right, that was the last question. So thank you, Mustafa, for a great
Sure.
presentation. This wraps up our webinar for today. If you all can please take 2 minutes of your time to fill out the feedback survey form. We would really love to hear from you. Again, thank you very much for attending. Be safe.
Thank you very much, everybody, and I hope it was of some use to you guys. And if you have any questions, please feel free to contact Serena. I can answer your questions afterwards in a written form. So any questions you may have, please feel free. Thank you very much.
Okay, thank you.
Thanks, Serena.